All right, so today we are talking about conductors and insulators. And real simple, nothing complicated. And so remind me, guys, we said we've talked about what a conductor is and what an insulator is. A conductor of electricity is something that what? It lets electricity move through it. Okay, and an insulator would be something that does not let electricity flow through it. And so there's two things we're going to look at to determine whether something is a good conductor or not. And the first thing is going to be the type of material. Okay, and the second thing is going to be the temperature of the material. Under types of materials, guys, we're going to have really three categories that we're going to consider. You know, we have metals, metalloids, and nonmetals. In terms of conducting electricity, guys, metals, good. Metalloids, meh. And nonmetals, we'll have a... Okay. One exception with nonmetals would be carbon, yeah. And the specific allotrope of carbon graphite. But no. Okay, so in terms of materials, guys, if we're looking up at the periodic table for these three, reflect back to chemistry, and you're going, oh Lord, it's been ages ago, but maybe some of you will say, well, I actually learned something in chemistry. Reflect back to chemistry. Looking at our periodic table, guys, what side of the periodic table gave us the metals? The left, right? So we had metals on the left, and on the right was the non-metal. Kind of right along the line, we got the metalloids. And when we had ionic bonding, we said which side tended to give up the electron? Which side gave up the electron, the metal or the non-metal?
It's been a while.
The metal, okay. The metal gave up its electron. And because you remember that this would have like 2 in the valence, and this would have like 6, and so this would take the 2 and that would make a full 8, and then we would have none. Okay, remember that? Okay, so the metals tended to give up electrons, the non-metals tended to hoard electrons. Okay, so let's go back to that. In order for something to conduct electricity, electrons have to travel. Electrons have to move. Okay, so the reason why metals tend to be good conductors is because in metals, electrons can travel, which is the same thing we see with ionic bonding. With ionic bonding, the metals tend to lose their electrons. And so what that comes down to, guys, is metals have weak attraction to their valence electrons. Okay, so you go up to a metal, you say, "Can I have an electron?" Sure. Okay, not really NBD. Okay, and in fact, guys, some metals have such a weak attraction to their valence that they generate something called an electron soup. And in these metals, if I had a big block of metal, we would say that those electrons are so weakly attracted to their nucleus that they really, we don't even associate. I mean, we don't even associate this electron with this atom or this electron. It's just like the electron just kind of float around. Okay. So in our best conductors, that's what we see. The electrons just kind of doing whatever they want. Okay. So with metals, good conductors, not really much problem. With metalloids, okay, metalloids can be, okay, conductors. But aluminum would be the aluminum's kind of that tricky one. That's kind of but aluminum conducts no problem. But to make a metalloid into a good conductor, we can do a process called doping. And my last class really enjoyed that word too. I don't know why. Huh? Okay. And and doping is adding stuff. We're gonna go with that real great descriptive word. To change their conductance. Okay, so one example of that. Water is a very poor conductor of electricity, and many people freak out anytime you associate electricity with water. But here I have a battery, and I'm going to clip it onto this light. I guess I just said light. I don't know. That's my favorite country word to say. Light. I only say it in the classroom. If I'm at home, I don't say, "Hey, turn on." I don't say, "Hey, could you turn on that light?" All right. So I have this dipped down in the water. If I take the other terminal and dip it in, we really don't see anything. Okay. The light does not light up. Okay. That's because water is not a good conductor, and so while a little bit of electricity is getting through that water, not enough to light up the light. Okay. So water's kind of meh. Okay. However, if I take water and I add some salt into it, okay, that can change the conductive properties of the water. Okay, so now what we see is, is when that is placed in there, we see that ample conductance is occurring to light that up. In fact, I mean, not really a huge difference.
Is that not dangerous?
I hope not.
Yeah, touch the water. With the battery getting in there, would it?
Let's try.
No.
Yes, try it. Try it.
It wouldn't shock you. Well, so you mean like if I put these two in the water and stuck my finger in there?
Yeah. Where's the button?
Please.
No.
Nothing. I'm fine.
Did you feel anything?
Well, then
Huh? I know.
I freaked out. Press the button.
Y'all would have felt bad, wouldn't you? I could just see me.
Oh, is that it right there?
I could see me sitting there convulsing, and y'all are saying, "Well, just press the button, get somebody in here." Should we push him over? Okay. So the first thing that affects whether something will be a good conductor is the type of material. And we said, metals best, non-metals. Okay. The second thing that's going to determine whether something is a good conductor is the temperature. And the rule is high temperature is bad. Low temperature is good. Okay. Typically when we discuss doping, that's in reference to metalloids, but I mean, personally, I would consider that the water to be a case of doping. I don't know what a professor at a university would say though. That's just me. That's what I would say. But similar same idea. So as temperature increases, what we see is it turns more into an insulator, and as temperature decreases, what we see is it tends to turn more into a conductor. Okay, so one application of that, I'm just going to draw a little line here so we don't get too confused. One application of that is with thermometers. Okay, with a digital thermometer, what I can do is I can have a loop of wire. And in that loop of wire, I'll just put we'll say that this little section right here is going to be copper or something. Okay, and I'll let that copper be exposed. And so I'm going to run some current through that wire, and I'm just going to measure how much current goes through. Okay, so with this was the water was an insulator. We saw not much current went through. With this is a conductor. More current goes through. Same battery, but different amount of current, right? Okay, so if the temperature is high, then what we're going to see is not much current goes through. And if the temperature is low, what I'm going to see is more current goes through. And all I got to do is figure out, okay, at 70, how much current goes through? At 75, how much current goes through? Map those, measure the current, and then I got a digital thermometer. Make sense? Okay. Temperature also is being investigated right now with something called superconductor. And a superconductor is something that has such a high conductance or such a high conductivity that we essentially say there's no resistance to the flow of electricity at all. Electrons flow through, no problem. Okay, there's no energy wasted there. I mean, kind of think of the mechanical equivalent would be something's rolling on the ground and there's no friction. Okay, that's kind of the same. Okay, and so for something to be a superconductor, typically the temperature needs to be low. Okay, for copper, I believe the temperature is negative 470 degrees Fahrenheit. Okay, so that's really cold. However, with they've been experimenting with ceramics now, and ceramics is like negative 300. Okay, where it becomes a superconductor, which happens to be the same temperature as liquid nitrogen. Okay, so if you take something and you surround it with liquid nitrogen and you keep the pressure on the liquid nitrogen high enough, then it would be a constant superconductor. Okay, why do you think that we don't use that like in the walls and yeah, it's expensive. I mean, yeah, I mean a certain you know you lose a certain amount of power and energy when you're running through just regular copper, but the amount of power and energy that you lose is nowhere near the amount that it would cost to put pipes that have liquid nitrogen in them with a ceramic conductor in the middle of it. Okay, that would be slightly expensive. So that's the reason why we're not using those. Okay, we good on conductors?